Today we are not talking about ordinary computers, mobiles, or laptops that we use every day. We are talking about something far more powerful, something that is slowly changing the future of technology itself. For decades, computer performance kept increasing because transistors kept getting smaller. From room-sized computers, we came down to laptops, then smartphones, and now chips so tiny that billions of transistors fit on a fingernail. But here is the shocking truth. This journey is reaching a physical limit. Transistors are now just a few nanometers in size, almost as small as atoms themselves. When technology reaches atomic scale, classical physics stops working properly. Heat, leakage, noise, and quantum effects start destroying reliability. This is where traditional computers hit a wall. And exactly at this limit, a completely new type of computer is born, not based on size, but on the fundamental behavior of nature itself. That computer is called the quantum computer. To understand quantum computers, we must forget everything we know about normal computers for a moment. Classical computers work using bits, and every bit can only be in one of two states, 0 or 1. Everything you see on screens, videos, games, banking apps, hacking tools, encryption, and even artificial intelligence runs on this simple binary logic. But nature does not work in binary. At the atomic level, particles behave in strange ways. An electron is not just a particle, it behaves like a wave. It can exist in multiple states at the same time, a phenomenon called superposition. When two particles interact deeply, they can become entangled, meaning the state of one instantly affects the other, no matter how far apart they are. Quantum computers use these natural behaviors directly. Instead of bits, they use qubits, which can be 0 and 1 at the same time. This single change multiplies computing power beyond imagination. Here is where it gets mind-blowing. A classical computer must try calculations one by one, step by step. A quantum computer explores all possibilities simultaneously. Problems that would take classical supercomputers thousands of years can be solved by quantum machines in minutes or even seconds. This power can break modern encryption, simulate molecules perfectly, design new medicines, optimize logistics, predict climate systems, and revolutionize material science. But this power comes with a price. Qubits are extremely fragile. Heat, vibration, radiation, sound, or even tiny electromagnetic disturbances can collapse quantum states in microseconds. That is why quantum computers operate near absolute zero temperature, around -273 degrees Celsius, in ultra-clean, isolated environments that look more like space laboratories than computer rooms. Companies like Google, IBM, Microsoft, and Intel are racing to stabilize qubits, increase their numbers, and control errors before this technology escapes the lab and enters the real world. We are still at the very beginning. Today's quantum computers have tens or hundreds of qubits, while truly world-changing machines may require millions. Yet even now, they have already achieved quantum supremacy, solving problems classical machines simply cannot. In the future, quantum computing will reshape cybersecurity, artificial intelligence, drug discovery, financial modeling, space exploration, and even our understanding of reality itself. Classical computers will not disappear, but they will become tools of the past, while quantum machines handle problems beyond human intuition. This is not science fiction. This is happening right now. Just like electricity once transformed the world silently before anyone understood it, quantum computing is quietly preparing to rewrite civilization. And the people who understand it early will not just watch the future, they will control it. Now here's the part most people don't realize. Quantum computers are not just faster computers, they think in a completely different way. A classical computer increases power by adding more transistors, more cores, and more electricity. A quantum computer increases power exponentially just by adding one more qubit. With every extra qubit, the number of possible states doubles. 10 qubits can handle 1,024 states at once. 20 qubits handle over 1 million. 50 qubits cross a quadrillion possibilities simultaneously. This explosive growth is why governments, military agencies, and tech giants are investing billions. If a powerful quantum computer becomes stable, today's encryption systems, banking security, passwords, crypto wallets, even national defense codes, can become useless overnight. That's why quantum research is not just about speed. It's about control, trust, and global power. But quantum computing is also extremely dangerous if misunderstood. One small disturbance, heat, vibration, sound, or radiation, can destroy calculations instantly. The science is powerful, but the engineering challenge is brutal. Despite these challenges, progress is accelerating fast. IBM has already crossed 127 qubits. Google has demonstrated quantum advantage. China is aggressively building quantum communication networks that are theoretically unhackable. Quantum cryptography, quantum internet, and quantum sensors are already emerging. In medicine, quantum simulations can model proteins perfectly, helping design drugs in weeks instead of decades. In materials science, they can discover superconductors that work at room temperature. In artificial intelligence, quantum systems could train models millions of times faster. This is not about replacing humans. It's about giving humanity tools powerful enough to solve problems we currently call impossible. What makes this story even more fascinating is that quantum computing forces us to question reality itself. Superposition and entanglement are not tricks. They are how the universe actually works. Quantum computers don't break physics. They obey it more honestly than classical machines ever did. We are no longer forcing nature to behave digitally. We are finally learning to compute the way nature itself computes. That's why quantum computing is not just a technology upgrade. It's a philosophical shift. It teaches us that certainty is an illusion, probability is fundamental, and reality is far stranger than logic ever imagined. The future belongs to those who understand this shift early, because the next revolution won't be loud. It will be silent, cold, and unbelievably powerful. Now let's talk about why quantum computers feel almost unreal compared to classical machines. In normal computers, every calculation follows a fixed path. Input goes in, logic gates process it, output comes out. But quantum computers don't follow one path. They explore many paths at the same time. This means they don't just calculate faster, they calculate differently. Imagine trying to unlock a password with 1 trillion combinations. A classical computer checks one key at a time, no matter how fast it is. A quantum computer, using superposition and interference, tests all meaningful combinations simultaneously and amplifies the correct answer while canceling the wrong ones. This is why problems like prime factorization, complex optimization, and molecular simulation suddenly become solvable. What looks impossible in the classical world becomes natural in the quantum world, because quantum machines don't fight uncertainty, they use it. But this incredible power also creates fear, especially in cybersecurity. Almost all modern encryption relies on problems that are hard for classical computers, like factoring large numbers. Quantum algorithms, especially Shor's algorithm, can crack these systems dramatically faster. This means banking systems, government databases, private communications, and even blockchain security could become vulnerable. That's why scientists are racing to develop post-quantum cryptography, new encryption methods designed to survive quantum attacks. Ironically, quantum technology itself offers a solution through quantum encryption, where any attempt to spy automatically destroys the message. In the future, quantum computers will both break and protect security, making trust a central issue of the digital age. Quantum computing is also changing how we think about intelligence and creativity. Artificial intelligence today relies on massive data and brute force optimization. Quantum AI could explore solution spaces that classical AI can't even represent. This could lead to breakthroughs in climate prediction, traffic optimization, financial modeling, and even understanding the human brain. But it also raises ethical questions. Who controls such power? Who benefits from it? And who gets left behind? History shows that every major technological leap creates winners and losers. The difference with quantum computing is scale. The gap between those who understand it and those who don't could be larger than any digital divide we've seen before. In the end, quantum computing is not just about machines, it's about mindset. It forces us to accept that reality is probabilistic, that certainty is limited, and that complexity cannot always be simplified. We are standing at the edge of a revolution similar to electricity or the internet, but quieter and deeper. Right now, quantum computers sit in laboratories, cold and fragile. But so did the first computers once. When this technology matures, it won't announce itself with noise. It will simply change everything underneath. And years later, people will look back and wonder how the world ever functioned without it. The future is being written at the quantum level, and whether we understand it or not, it's already moving forward. At this point, one important misunderstanding must be cleared. Quantum computers will not replace your phone, laptop, or gaming PC. They are not designed for everyday tasks like browsing, video editing, or social media. Classical computers are excellent at stable, repeatable operations, and they will remain essential. Quantum computers are specialists. They are built for problems where possibilities explode beyond control, where classical logic collapses under complexity. Think of quantum computers not as faster cars, but as spacecraft designed to travel where roads don't exist. This distinction matters because it defines how society will integrate quantum technology, quietly, behind the scenes, powering breakthroughs rather than replacing consumer devices. Another fascinating area where quantum computing shines is chemistry. At the quantum level, molecules don't behave like neat diagrams in textbooks. Electrons interact in deeply complex ways that classical computers approximate but never fully capture. Quantum computers, however, speak the same language as molecules themselves. This allows scientists to simulate chemical reactions with near-perfect accuracy. The result could be revolutionary medicines, cleaner energy solutions, better batteries, and materials stronger than steel yet lighter than plastic. Entire industries could transform, not because of faster computers, but because we finally understand nature on its own terms. Quantum computing also forces humanity to rethink randomness. In classical systems, randomness is usually fake, generated by algorithms pretending to be random. Quantum systems, however, produce true randomness, born directly from the uncertainty of nature. This has massive implications for cryptography, gaming, simulations, and scientific modeling. True randomness improves fairness, security, and realism. In a strange way, quantum computers teach us humility. They remind us that not everything can be controlled, predicted, or simplified. Looking ahead, the real revolution may not come from a single quantum computer, but from quantum networks. Scientists are already experimenting with quantum communication, where information is shared through entangled particles. This could lead to a quantum internet, an entirely new layer of communication that is inherently secure and fundamentally different from today's networks. Messages could be transmitted with security guaranteed by the laws of physics themselves. Once again, this is not science fiction. Early versions already exist, and progress is accelerating faster than most people realize. One of the most misunderstood aspects of quantum computing is time itself. Classical computers feel fast because they complete billions of operations per second, but they are still prisoners of sequential time. Quantum computers bend this idea by allowing calculations to exist in overlapping states. This doesn't mean they travel through time, but it does mean they compress decision spaces in ways classical logic cannot. Problems that require exploring countless futures suddenly collapse into a manageable present. This is why quantum computing feels like cheating. It doesn't break rules. It simply plays the game on a deeper layer of reality where time and probability are tightly woven together. Education will also be forced to evolve. The way we currently teach computers, coding, and logic is built on deterministic thinking. If this, then that. Quantum thinking demands a new mindset where outcomes are probabilities, not certainties. Future engineers will not just write code. They will design probability landscapes. Debugging won't mean fixing mistakes. It will mean shaping outcomes. This shift will separate future creators from future consumers. Those who learn to think probabilistically will shape technology, while others will only use it without understanding what's happening underneath. There is also a silent economic race happening right now. Countries that master quantum computing first will dominate finance, defense, healthcare, and communication. This is why governments are funding quantum research at levels similar to nuclear and space programs. Quantum advantage is not just technological, it's geopolitical. Control over quantum algorithms could decide trade, security, and even global stability. The next world powers may not be decided by armies or oil, but by who controls computation at the deepest level of physics. Yet, despite all this power, quantum computing humbles us. It reminds us that reality is not binary, that certainty is rare, and that complexity is natural. For centuries, humans tried to force the universe into simple rules. Quantum science shows us the opposite. The universe is rich, layered, and beautifully strange. Quantum computers don't simplify reality, they respect it. And that is why they represent not just the next step in technology, but a new relationship between human intelligence and the universe itself. As quantum computing moves forward, one unavoidable question rises. How close are we really to practical, everyday impact? The honest answer is closer than most people think, but not in the way movies show it. Quantum advantage will first appear quietly inside data centers, pharmaceutical labs, climate research institutes, and national security systems. Ordinary people may not see a quantum computer directly, but they will feel its effects. Just like electricity existed long before every home had a socket, quantum computing will power the background of civilization before it ever becomes visible on the surface. Another powerful outcome of quantum research is how it reshapes classical technology itself. While building quantum machines, scientists are discovering better ways to design classical chips, reduce energy loss, and improve error correction. Even if quantum computers took longer than expected to mature, the research alone is already upgrading existing systems. In that sense, quantum computing is not a gamble. It's a guaranteed accelerator of innovation. There is also a deeply human side to this story. Every major technological leap begins with confusion, fear, and resistance. People once feared electricity, radio waves, airplanes, and even the internet. Quantum computing is no different. It sounds abstract, intimidating, and unreachable, but that is exactly why understanding it matters. The people who learn early gain clarity, confidence, and opportunity. History favors those who adapt before change becomes unavoidable. Quantum computing is not replacing human thinking. It is amplifying it, giving us tools to ask questions we never had the power to answer before. In the end, quantum computing represents a turning point, not just for technology, but for human perspective. It shows us that the universe is not rigid, not predictable, and not limited to simple rules. It rewards curiosity over certainty and exploration over control. The future will not be decided by who owns the biggest machines, but by who understands the deepest principles behind them. And those principles are no longer hidden. They are waiting to be learned. One of the most exciting things about quantum computing is how it changes the idea of problem solving itself. In the classical world, we try to simplify problems because complexity is expensive. In the quantum world, complexity becomes a resource. This flips centuries of engineering thinking on its head. Instead of breaking problems into smaller pieces, quantum systems embrace the whole picture at once. This is why quantum computing feels almost alive. It doesn't fight complexity, it swims inside it. Another area where quantum thinking will quietly reshape society is decision-making. Today, governments and corporations rely on simulations that simplify reality because exact modeling is impossible. Quantum computers can model uncertainty directly. They don't give one perfect answer. They give probability distributions that show what is likely, unlikely, and dangerous. This allows better risk assessment in finance, disaster prediction, climate policy, and supply chains. Quantum computing also exposes a hard truth about the future workforce. Many jobs won't disappear overnight, but the value of skills will change. Routine problem solving will become less important than creative thinking, interpretation, and ethical judgment. Quantum machines can calculate faster than any human, but they cannot decide what should be calculated or why it matters. Humans will still define goals, values, and meaning. There is a poetic irony in all of this. Humans began computing by copying logic, simple yes or no decisions. Now, at the peak of our technological journey, we are returning to nature's logic, uncertainty, probability, and connection. And this is why understanding quantum computing is not optional anymore. You don't need to build one. You don't need to code algorithms. But you must understand what kind of world it creates. Every generation faces a moment where knowledge divides society into leaders and followers. Quantum technology is one such moment. Those who understand it early will guide decisions, investments, and innovations. So when you hear the words quantum computer, don't imagine a machine locked in a laboratory. Imagine a future quietly reshaping medicine, security, energy, and intelligence itself. Imagine answers appearing where questions once seemed unsolvable. Imagine a world where uncertainty is no longer feared but harnessed. That world is not coming. It has already begun forming. And the only question left is whether we choose to understand it or simply watch it unfold from the outside.